Welcome all of you. Since last 2 or 3 classes, we have been discussing about carbon 13 NMR. Especially in the last class, we discussed about the analysis of the carbon 13 spectra, varieties of nuclei. I also explained to you about substitution effect and how to predict a chemical shift. It is possible, especially for the phenyl rings. I took the example, and for different places or different positions of the phenyl ring, when the substitution is there, its effect at the ortho, meta, para position or ipso positions is already well documented. We can utilize these values from the table, take benzene value as the base value, and then add up all these values together, whether it is add or subtract depending upon the contribution, and the final chemical shift value can be predicted. And we took several such examples. And afterwards, we also went to the analysis of the carbon 13 spectra fairly by looking at the intensity pattern and the chemical shift positions. And we wanted to see the heteronuclear coupling in carbon 13 spectrum, especially when we are looking at carbon 13 directly, when you are detecting carbon 13, though it is the abundant spin, dilute spin, the question of satellite does not arise at all. We are directly detecting the carbon 13. And it is coupling with abundant spins like phosphorus and fluorine we wanted to see. We took 1 or 2 examples of the molecule like pyridine, and we wanted to find out what is the coupling constant, how we can analyze the spectrum of the carbon 13 spectrum with proton decoupling, so that we are going to get only carbon fluorine couplings. We use that and analyze that. And of course, CF3COOH is another thing which we took an example. And the carbon directly attached to fluorine was a quartet, we could make out, and the COH carbon also was a quartet because of 2 bond coupling. We knew how to analyze simple carbon 13 spectra from the information that is available from the multiplicity pattern and using chemical shift, and we know how to extract the heteronuclear couplings. We can continue further now with another 1 or 2 examples before going further. And now I will take the example of coupled carbon 13 spectrum of methyl trifluoroacetate in CD3OD, and this is the carbon 13 spectrum, and every peak here is genuine peak. Now our job is to identify and make the assignment which peak correspond to which. Of course, molecule is this one, methyl trifluoroacetate, and of course we are looking at the carbon 13 spectrum fully coupled, it is not decoupled. So that means you have fluorine carbon coupling and also proton carbon coupling both simultaneously present. That is why I took this example, so that we should know how to interpret such spectra. Where do you start with? Of course, there is a quartet at 0 frequency, 0 ppm. Obviously that was the reference we use, that is TMS, and TMS Ca3 the 3 protons split that carbon into a quartet. That is what I told you already, for different carbons having different protons attached, Ca3, CH2, CH and quaternary carbon, how we get the multiplicity pattern, quartet, triplet, doublet and singlet, I discussed. Obviously this is a TMS which is giving a quartet. What about this one? This is CD3 part of the acetonite, the CD3CO CD3. So that is a multiplicity pattern which you are seeing, this is a solvent peak. Then what are the remaining peaks? Of course, remaining peak of, you can look at it, this is a CF3 carbon and it is a long range coupling is there, not CF3 carbon, this is a CF3 carbon, there is a one bond coupling is there, carbon fluorine, which is quite large, about 264 hertz, and a large split quartet coming because of 3 fluorine atoms chemically equivalent. So this one carbon is going to be a quartet. I fairly assume this is a 1 bond carbon fluorine coupling quite large, and this is CF3 group coupling with carbon. What is the next one? If you look at the next one, we can start making the assignment. This is carbon 1, and I would say this is carbon 3. Okay, that is carbon 3 is fine. Why is a quartet? See, remember there is 1, 2, 3, 4 bond coupling with the fluorine, which may not be reflected in the spectrum, which may not be there at all. So this carbon is a quartet because of its coupling with Ca3 protons, 3 protons. As a consequence, it is a quartet. But what you get here, if you measure, is the CH coupling, here you got CF coupling. So that is fine. And if you look at the carbon 2, something interesting is happening. Look at the carbon 2, it is a quartet, fine. I can say this could be because of the 2 bond fluorine coupling, and also it could be coupling with these 3 protons, we do not know. But I would fairly say it is 2, but if you expand this one, you can see each lane of the quartet is a quartet. Again, it is quartet of quartets. Fantastic. So that means this carbon is experiencing coupling with both CF3 group and CH3 group. So CF3 fluorine couples this. This is a coupling because of the fluorine. It is a large quartet of the order of 42 Hertz approximately. And each lane is a quartet because of the long range coupling with CH3 protons. That is very clearly understandable here. Okay, we can make assignment. Of course, this is TMS, this is solvent. What is this last peak left over? This is solvent carbon CO, which is not split because of any other reason. Okay, that is a solvent carbon. And very clearly we could assign all the peaks here in a simple molecule, and we could get both homonuclear coupling, both heteronuclear coupling, carbon proton and carbon fluorine here. This 1JCF, this is 1JCH, this is 2JCF plus 3JCH is there, this is 1JCD, TMS and this. So, we will go further and look at, so far we saw the fluorine coupling. What happens if there is a phosphorus present? And another example of a simple molecule I am taking. This is the molecule which is spectrum of diethyl ethyl phosphonate. This is the molecule, and now we can see there are 2 CH3, 1, 2 and 3. 3 CH3 CH2 groups are present and a phosphorus is here. And if you look at the spectrum carefully, but look at the title here, it is proton decoupled. So, there is no carbon proton couplings present here. If at all there is any multiplicity coming, it is because of coupling with phosphorus, that we should know. Okay. So, each of them is expanded here. See, this is a doublet, this is a doublet and this is a doublet, and of course, this is obviously 3 line pattern of equal intensity because of coupling with deuterium. This is CdCl3 solvent, that is also clear. So, each of the 3 carbons, there are 3 different carbons here and each of them is a doublet here. Of course, I have written 1, 2, 3 and 4, this is also there. We will see now, first one is a doublet, that is because of coupling with this phosphorus 1, 2, 3 bond coupling is there. Okay, it is a doublet. Of course, phosphorus is a spin off nucleus. As a consequence, carbon peak is split into a doublet. Now, this is another one, this is carbon 2, and of course, this is also having a coupling with phosphorus, 2 bond coupling. Look at this one, this is the third one which is directly bonded to phosphorus, carbon 3, which is expanded here, and that splitting is quite larger. You can see this is also a doublet, very easy. And last one left over, if you expand this one, this is carbon 4 here, and thus that also has 2 bond coupling with phosphorus. Of course, protons are decoupled. So, each peak is a doublet. From the coupling strength, you can also make the assignment very easily, because 1 bond coupling is quite large. This is that one, and then of course 2 bond and then 3 bond, like this we can make the assignment, and you can measure the couplings also. So, you can very easily see that 1 bond carbon proton coupling here is about 140 Hertz, and of course 2 bond is 7 Hertz, 3 bond is 6 Hertz, another 2 bond with the other carbon is 7 Hertz. Continuing further, we will take another example of 2 molecules where we can extract carbon 13 and phosphorus coupling in this molecule. Again, this is a proton decoupled spectrum. As I have been always telling you, if the nucleus is put in the flower bracket, that means that nucleus is decoupled with the nuclei which you are detecting. So, we are detecting carbon 13 decoupling proton. Obviously, carbon proton couplings are not present in the spectrum. So, now we can look at it very carefully. There are 2 molecules. Look at this molecule, and this molecule, of course, we will start with this molecule which is highlighted here, and this molecule we have, see, 1J coupling is there, 1J carbon phosphorus coupling. It is quite large, it is of the order of 65 Hertz approximately. This corresponds to carbon 7, and of course, there is also another 1JCP which is for carbon 2 and 6, both of them having 1 bond coupling, and it is here. It is of the similar order, of the order of 63, 64 Hertz. This is carbon 2 and 6 are identical, so it is getting like this. Then what about this one? This is a 2 bond coupling. This is 2 bond coupling with carbon 4, you can see here, 2 bond coupling, and then 3, you can take other coupling with carbon 3 and 5, again it is 2 bond coupling. So, all the each of the carbon P here is a doublet because of its coupling with phosphorus. Very easily you can assign and extract the coupling information by doing proton decoupling. If there was no decoupling, this would have been a very complex spectrum, very difficult to extract both carbon proton and carbon phosphorus coupling. Now coming to this molecule, again one bond coupling is of the similar order, 64 Hz, this is one bond coupling, and then you can have another one 2 bond coupling, another 2 bond 3 bond coupling is there. There are 3 different types of this thing is 1 bond coupling and 2 bond and then 3 bond coupling, everything we can easily measure it. Okay, this is between coupling of carbon with abundant spins phosphorus and fluorine. What about coupling between carbon and low abundant spins? Carbon itself is a dilute spin. When I said when I am detecting that, we do not have to worry about it as dilute spin, we are directly detecting it. Only when it is coupled to abundant spin we are worried about satellites. Now we are directly detecting, but can that give satellites because of coupling to other heteronuclei which is less abundant? Of course it can give rise to satellites. Let us take 1 or 2 examples of that. Look at this molecule, this is dimethyl mercury, a neat sample is taken, no, it is not dissolved in any solvent, and this is a mercury carbon 13 NMR. If you see, we have mercury has several isotopes, usually mercury 199 is what we have to consider, 201 and others is not being, it is very difficult to detect. So mercury 199 is the nuclei of our choice most of the time. So that is going to give rise to the abundance of approximately 17%, and that can couple to carbon 13 and give rise to satellites. See, this is the main peak coming because of the carbon attached to CH3, and this carbon, of course we have decoupled proton, is coupled to mercury He199, and look at this is a fairly big intensity satellite because abundance is close to 17%, and so mercury coupling to carbon here appearing as satellites. So measure this separation between these 2 satellites, you are going to get 1 bond carbon mercury couplings, which is fairly large, of the order of 686 Hz. I told you in some cases of some heteronuclei, the coupling can be of the order of several hundreds, even 1000 Hz, several thousand Hz. So this is a large coupling between carbon and mercury 199. We will go to the other molecule. It is a carbon 13 NMR of tributyl tin iodide. Here tin is coupling. Tin has 2 isotopes. Interestingly, tin 115, of course 115 is also there, that is very low, we can ignore it. 117 and 119 are the 2 things which we have to consider. Both are interestingly spin off nuclei, and abundance is almost equal, 8.6 and 7.7%, nearly equal, you can say both of them are approximately 8%. And in this molecule, if you are looking at the carbon 13 spectrum of it, look at it, what is the type of spectrum you are going to get. First, of course, this is a CH3 peak, and you can as well see this is not a this one, this is a CH3 group, and there is no multiplicity being shown here. So that means it is not decoupled, I mean it is coupled. There is a multiplicity which is, if you expand you can see it, it is not shown here. So this is CH3 carbon, we know that one. And of course next is this one, CH2 carbon attached to tin, directly bonded to tin. And this, interestingly, if you look at this one, if you expand this CH2 carbon directly attached to tin, this is expanded here. You can see 2 peaks on either side. They are satellites of tin coupling to this carbon of CH2. They are nearly of equal intensity, as I said, abundance is almost similar, and the couplings are different. One is tin 117 coupling to carbon, other is tin 119 coupling to carbon, which we can find out very easily, that is not a difficult thing. Now next come to this carbon. This carbon is like this, and it is this CH2 carbon. Again, if you see on either side, you are going to see satellites. Okay, and there are 2 peaks here. So okay, you can very clearly see, and of course this is, if you go further, another CH2 is there. This CH2 is coupled to tin, and that coupling is here, and it is not very well resolved to show coupling between both the different types of tin, 117 and 119, where it is clearly seen here. Can we make use of carbon 13 NMR for the structural assignment simply without using proton NMR? At times, very easily, you can just looking at the carbon 13 NMR, you can arrive at the structure of the molecule. How do we do that? Let us take the example of this molecule. This is the carbon 13 NMR proton decoupled spectrum of this molecule. There is a name for this molecule. First we have to make the assignment of all these things. First thing, the challenge is to identify the position of CF3. Whether CF3 is here, here, here or here, we do not know. Can we make an assignment or get the structure of the molecule based on this carbon 13 spectrum? That is the challenge we have to answer. Okay. Of course, first assignment we know this is CdCl3, because the CdCl3 3 lines of equal intensity because of carbon coupling to deuterium, that I have been telling you. And if you look at it, this is CH2 carbon is coming at the center between 2 sulfur, it is CH2 carbon. I can say fairly it is there is no other coupling possible for this one. So, it is that one, fine, that is a CH2 carbon. Remaining part, this low field region is expanded here. If you carefully see, a lot of information you can get out of it. If you see, there is 4 peaks here of intensity 1331. What is this one? This is carbon of CF3 group, carbon 13 of CF3 group. The 3 fluorines are splitting this carbon into quartets of intensity pattern 1331. That is what it is. So, we can make the assignment for this to the center of this quartet is the chemical sheet of CF3 carbon. So, we can make the assignment of that. Okay. One bond coupling is quite large also. And next is there are the 3 other carbons C1, C6 and C5. Here C1, C6 and C5, and all of them appear to be singlets. Of course, C1 is a ipso quaternary carbon, is very weak in intensity, that we can make out from the intensity itself, and C5 and C6 are here and they are singlets. That clearly shows this long range coupling of fluorine to these 2 carbons are not there. That is one conclusion you can draw. But what about other carbons 2, 3 and 4? Look at it, this is a carbon 3 I would say, which is directly attached to CF3 group, this carbon, and this is also a quartet because of this 3 fluorine. This is a large coupling here, large quartet, but this is 2 bond coupling which is quite small, but still it is a quartet and measurable quantity. Okay, I would fairly say that is I can make the assignment confidently as C3. And of course, C2 and C4 both of them are separated by 1, 2, 3 bonds away, 2 bonds coupling is there, and they are again the quartets. Each of them is expanded here. You can see that it's if you see 4 peaks here, 4 peaks here, 1, 3, 3, 1 quartet. So, this is 2 bond, this is 3 bond CF coupling. Look at it, 3 bond CF coupling is more or less of the order of 3 to 4 hertz, very small, and it is not well resolved, but still you can make out the quartet structure in both of them. So, I can confidently say 3 bond coupling, this is C2 and C4. Which is C2, C4? Of course, I already told you, we know how to do that. We can make the rough estimate of that. And this is again 2 bond coupling, we can clearly say this is C3. A sort of assignment is made. There is this clearly tells me there is one CF3 group and there are 6 carbons present in this molecule. From the analysis, there is one CF3 group and there are all these remaining 6 carbons are there, and I have 5 here and CH2 in the previous one I showed you. What are the observations? We can draw the conclusion here. One, the structure must be symmetrical. Why do I say that? If the structure is not symmetrical here, look at it, then the CF3 group, if it is somewhere here without any symmetry, then the number of carbons would have been more. Otherwise, we would have got CF3 2 peaks. Because of symmetry, chemical equivalence is there and only one CF3 group is observed with quartet. That is fine. So, CF3 is also not in the para position. Why do I say that? If it was to be in the para position, the symmetry would have been reduced. For example, instead of here, if CF3 would have been here, then what would have happened? This carbon has chemical equivalence and this carbon has chemical equivalence. Then the number of carbon instead of I said one CF3 and 6 carbons are there. If there was a symmetry, if it was in para position, with respect to S, I am talking with respect to sulfur, in which case you would have got one CF3 and only 4 carbon peaks, not 6. Very fact we are getting 6 carbon peaks. Another conclusion I can draw is this is not in the para position. Okay, we have drawn already 2 conclusions. One, there is only single CF3 and there is a symmetry here Because of that we are getting single CF3, and this CF3 is also not in the para position with respect to sulfur, otherwise the number of carbons what we observed would have reduced. Instead of 6 we would have got 4 peaks. Go further, CF3 is also not in the ortho position, I will say here. It is also not ortho with respect to this. Why? Very easily you can come to a conclusion. This CF3 is coupled to this and also these two carbons. If it were to be here, this carbon would have coupled to fluorine. Otherwise, the CS carbon would have been split by CF3 group into a quartet with a long range coupling. But CF3, this carbon 1 is the carbon attached to S sulfur is still a singlet. That means I can conclude easily say CF3 is not ortho to CS carbon. So it is not para, it is not ortho to CS carbon. Then what is the other option? It must be meta to CS carbon. So the correct structure from the carbon 13 spectrum interpretation I can draw is this one. So that means from the simply looking at the carbon 13 spectrum, number of carbons and this multiplicity pattern with for each of the carbon with coupled to fluorine, I could draw a conclusion. This is the structure of this molecule. Very easy. So we can utilize that. Going further, I want to tell you one important experiment called DEPT. This involves what is called a polarization transfer. As I said yesterday, polarization transfer I am going to discuss that later, because I have not discussed this polarization transfer and NOE, which I introduced yesterday while doing the decoupling NOE factor. I said these two terms I mentioned but not discussed in detail, which I am going to do it in next class or subsequent classes. But right now understanding of that is not important, but please remember there will be a polarization transfer, which means we will transfer the polarization or the magnetization from abundant spins to rare spins. When we do that, what will happen? The dilute spins intensity will go up. We will enhance the signal intensity. It is like robbing the rich, paying the poor. Take the magnetization from proton and give it to carbon which is dilute spin. And now using this polarization transfer technique and also by using an experiment called DEPT, a sequence, experimental sequence called distortionless enhancement by polarization transfer. Using this, it is possible for us to identify different carbons attached to different protons. For example, I can point out what are the carbons attached to CH3, what are the carbons with CH3 protons attached, 2 attached, 1 attached and quaternary carbon. So all CH3, CH2, CH and quaternary carbons, only 4 types of carbons would be possible. They can be identified by using distortion, DEPT, distortionless enhancement polarization transfer. So the two new concepts I told you, we will NOE in polarization we will discuss in the subsequent classes. Why we require DEPT? What is the need of a DEPT? Look at this molecule which we discussed earlier also, carbon 13 spectrum. This is a coupled, this is decoupled. Even in the decoupled spectrum, so many peaks are there. What can you make out of this? In the first approximation, I will say this is a quartet peak, this is a CH3 carbon, I would say. Okay, further I would say there are 2 doublets here. Then I would say these are 2 CHs. This could be a CH which is a doublet. Beyond that, from this region, what can we say? Except 1 or 2 carbons here, what can we say about these carbons? What is the multiplicity pattern? Which is CH3, which is CH2, which is CH. So it is very difficult to identify. Only in this molecule, a couple of CH3s and couple of CH2s will be observed. We can identify. What about other carbons? How do you identify them? For that, we use a pulse sequence called DEPT. DEPT is an experiment, very simple experiment. What we do is, we apply carbon 13 pulse 90 180 and then on the proton channel 90 188 theta pulse. This is a sequence. Do not worry about how it works and everything, because we have discussed this in one of the previous courses. What is important is angle theta of the last pulse on the proton. In the proton there are 3 pulses. We are worried about only last pulse, the theta degree pulse on proton. And this is the angle with which we are going to tilt the magnetization using this theta is called the flip angle of the pulse. This flip angle can be different. We can keep it constant and vary it. So what we can do is, we can do the polarization transfer by transferring proton magnetization to carbon 13, and advantage is we can get the experimental time reduced by 1/16. Very interesting. See, if an experiment takes 16 hours, by using depth you can do the polarization transfer, you can reduce it to 1 hour. Great reduction in the experimental time. We can do that. So, how do you identify this? We have to do 3 experiments. In principle 2 are enough, 90 and 135, but in some books and others people mention 3 experiments. I am explaining all the 3, but practically you require only 2 experiments. So, in the third proton pulse is there, flip angle pulse theta, which I showed in the pulse program. We can do 3 experiments with keeping angle theta as 45 degree, 90 degree and 135 degree. 3 things we can, 3 experiments we can do. And based on these 3 experiments, the phase and the intensity of the carbon peaks vary. They depend upon the flip angle of the last pulse. Depending upon whether you have 45, 90 or 135, the phase of the pulse, phase of the peak, whether it is positive or negative, and how this intensity, whether it is 0 or maximum, we can define, we can understand. And this pulse sequence tells us based on the intensity and the phases which carbon is which, whether it is CH3, CH2, CH like that. This is graphically I am showing like this. For example, if I do a flip angle pulse with a depth experiment, last proton pulse keeping 45 degrees. Remember, CH, CH3 and CH2 carbons all are positive intensity. On the other hand, I do a depth experiment keeping flip angle exactly 90. Now you see CH and CH3 intensity goes to 0. That means carbons with odd protons attached intensity goes to 0. Okay, I am sorry, correct, CH3 and CH2 goes to 0. Only single proton attached carbon 90, that will have full intensity. Only CH2 and CH3 goes to 0 and CH carbon have full intensity. Go further, 135 degrees you make it. Interestingly, CH3 and CH will be positive and CH2 will be negative. So, all you have to do is 2 experiments 90 and 135 and a conventional carbon 13 spectrum. You will be able to identify all the 3 carbons fairly easily. This is the table I have prepared for you. This is a conventional spectrum, all carbons are positive intensity. If you do depth 45, you do not see quaternary carbon because there is no polarization transfer. There must be directly attached carbon proton. So, all others are positive. If you go to depth 90, only CH is positive, all others are 0 in intensity. If you do depth 135, CH is positive, CH2 is negative, CH3 is positive. That is all we have to remember. Then you do an experiment on this chiral, on this cholesterol molecule. When you do that experiment, this is what I showed, a conventional experiment, not decoupled, fully coupled spectrum, and this is decoupled experiment. We do not know which carbon is which, whether it is CH2 carbon, CH3 carbon or CO carbon or quaternary carbon. We will see now the depth experiment of that. Very interestingly, I do with the depth experiment. This is a normal carbon 13, all are positive. Do depth 90. When you do depth 90, what did I say? You will get only CH carbons, all are CH carbons here. You do depth 135. What did I say here? Look at in this table. Depth 135, if you do, CH is positive, CH3 is positive, CH2 is negative. See here. Here, in the depth 135, CH and CH3s are positive and all CH2s are negative. I can say in the crowded spectrum, these are all CH2s and these are all CH and CH3s from the depth 135. Now, combination of these 2 experiments, taking the information from this and this, you can do complete assignment of all the carbons, whether it is CH3 carbon, CH2 carbon, CH or CH carbon can be done. Okay. So, this is what it is. The expanded region of that if I show, you will clearly appreciate the importance of this one. Look at this one here. Here there are 2 carbons, one is positive and the negative. This must be this is CH2, this could be CH. Here look at it very close by and you will not find the difference, especially here. See, one is positive, other negative, one is CH3, other could be CH2. So, this you will not be able to make out in the, if you look at the region of chemical shift, you will say it could be CH3 or it could be CH2. You do not know. So, only chemical shift information alone will not be able to tell you which carbon is this. But you say in the depth experiment, I am able to simply take care of this thing. And I can say which are the carbons which is attached to single proton or 3 protons and 2 protons. All CH2s will be negative in intensity with depth 135, all CH and CH3s are positive intensity. That is how it is. So, then one few experimental requirements are there for depth. Most important is 90-degree pulse has to be perfect like this. Only exact 90-degree pulse, only CH carbons will be seen. If it is slightly deviating, let us say instead of 90, you make 90 degree 5 degree, see already CH peaks appear negative, CH2 peaks. You can start getting CH2 peaks negative, which in principle you have to get only CH peaks, and all other peaks should go to 0 for 90, but other peaks start coming up. It can confuse you. Secondly, also you can go to this one. This instead of 95, make it 85 degree. Is exactly 90, all other peaks won't come. But if it is more than 90, CH2 peaks will be negative. But here CH2 peaks will be positive for less than 90. If it is 85 degree, even they are coming. It will confuse you to be CH carbons. So, for precise 90 degree is very important. Little bit of mistuning of the 90 degree, you get into problems. So, these are all CH2 carbons which appears positive. So, importance of probe tuning is very, very important for depth. Probe has to be tuned when the samples are changed from polar to non-polar, etc. And of course, there are two types of probes in the NMR: direct detection probe where 13C coil is inside, proton coil is outside. Indirect detection probe is there where inverse probe, proton coil is inside and carbon 13 coil is outside. And so, very important for all those things. So, for a direct probe, tuning is not very critical. You are directly you are see carbons you are seeing. For the inverse probe, tuning is very critical. If you do not do it properly, you will make a mistake, and you do depth 90, slight variation in the angle, you may get the CH2 peaks positive or negative instead of only CH peaks that get confused. So, depth experiment might fail with this thing. And also one bond setting of the angle is extremely important. For example, average CH point in all the experiment we take to be 150 hertz. It need not be, it can be more, it can be less also. But if it is, what happens if the CH is large, very large, or deviate significantly? This is what happens. Look at it. When this is the case where carbon 13 normal is there, and this is the carbon 1 here. Interestingly, this carbon CH coupling is very large, about 240 and 250 hertz. As a consequence, what is going to happen? This CH peak in the depth 90, we should see only its CH peak, that is not appearing here. That is what happens. If you go to depth 135, also it is missing. So, these type of errors will happen, and if you go like this, for example, this one, this will also come, this is starts appearing. So, some of these things there will be a big problem. If you look at this carbon CH2, the carbon 2, look at this one, this intensity. So, what is happening is mistuning of 90 degree, or if the angle is not J coupling is deviating significantly from the set value of 150 hertz, there could be experimental artifacts. So, precise setting of the J value is known. Sometimes if the J value is different, what you should do is you do 2-3 experiments. Okay, that is what it is. So, advantage of depth over inept is inept I have not explained to you, I will show you later. This is APT and this is depth 135. Depth has a lot of advantages, signal intensity is much better here. Okay, I will there are lots of things we can discuss about it. Depth 135 is much better than APT because of the intensity, there is a polarization transfer here. Okay. So, APT there is no polarization transfer, only depth there is a polarization transfer, that is the advantage. And lastly, I wanted to tell you one thing about how we can utilize depth in getting the structure of some one or two molecules. So, since the time is getting up, I am going to stop here. We will come back and just explain that one next, and then continue further with the analysis of the other spectra. So, in this class already we discussed lot of things about the analysis of the spectra, carbon 13 spectra, how to get the heteronuclear coupling in the abundant spin is present in carbon, with carbon coupling with abundant spin, carbon coupling with the rare spin, dilute spin like selenium that we saw, and many of the other examples like for example depth experiment, depth 90, 135, depth 45, how we can analyze in a crowded region, identify the carbons attached to single proton, 2 protons or 3 protons, etc., based on the intensity in the phases of the pulses. This is a depth experiment where the polarization transfer is involved. As a consequence, signal intensity goes up. Because signal intensity goes up, experimental time drastically gets reduced. These are the advantages of that. In addition to identification of different carbons, we can speed up the experiment. And I showed some of the examples of how we have to do the perfectly set the 90 degree for CH DEPT experiment, and how missetting of the J value can give rise to problems. These are all certain tricky issues which one should remember. With this I am going to stop. I will come back and continue with the remaining part later. Thank you very much.